Talking about tests of significance is just the coolest stuff ever. We, for the first time, start to really put things together, and we get to figure out like what's true, which is so important. It's going to be a series of videos for this. First one, concept of hypothesis testing. We're going to play a game. So we're going to flip a set of 10 coins, and if there are more heads than tails, then I win. If there are more tails than heads, then you win. Let's look at our coins. Here are our 10 coins. First flip, 7 heads. Looks like I won the first round. Maybe your luck will turn around there. Let's flip the set of coins again. 8 heads. I guess I win again. Let's flip the set. I'm sure you'll start winning soon. 7 heads. Oh, boy, I'm lucky today. Let's do it maybe one more time. 9 heads. I win yet again. At this point in time, I'm thinking that it's reasonable for you to start questioning whether these are fair coins. All right, have I rigged this game? Or are the coins fair? This is a really classic example of the kind of questioning that the hypothesis test gives you. So we have, on the one hand, the fact that improbable events, like getting those 4 flips, all very high number of heads, could occasionally happen. If we go back and look, could this happen due to random chance? Well, sure it could. But there's this sense that that's kind of improbable. But improbable events will occasionally happen. On the other side, we actually have that feeling that, something not random at all is going on. There is actually something different going on here, such as the coins not being fair. These two somewhat opposing points of view are in balance, right? We have to figure out where does this fall out. And to help us, it's really about this word, improbable. How improbable is it? So we can, with a little review of probability, calculate how probable or improbable, as it were, those coin flips really are. So we're going to do a little review of probability. So what's the probability of getting 7 and an 8 and another 7 and then a 9? Well, and is multiplication rule. We could figure out the probabilities. That's, of course, a binomial probability. So we can use the binomial PDF formula. We can get the probabilities of getting 7, 8, and 9. Right, we can plug those numbers in, multiply them, and we get this astronomically small number. Right, incredibly small probability. Now, we actually have to step back, and this actually I would consider to be an incorrect calculation. Nothing wrong with the numbers per se, but we set it up wrong. Let's look at, 5 and 5 and 5 and 5. That, in a sense, should be maybe the most probable. Right? We can get our binomial probability for getting 5 out of 10. One of the most probable outcomes is still less than 1%. What's going on here? Well, what we're doing here by mistake, right, is by using these ands, we're talking about just one combination. Now, there are over 1,000 combinations, some more probable than others, but there's still an awful lot of them. And if we're looking for this one specific combination, that's going to be a real small probability, regardless, just because there's so many. So let's rephrase the question. I hope you're enjoying the review of probability. Instead of getting those, specific flips, what's the probability of getting at least 7 heads showing 4 times in a row? So at least 7 heads showing on the first flip, right? 7 heads, 8 heads, 9 heads, 10 heads, all added up together. That's the at least. We can do that. That's just one flip. Now we're going to have 4 flips, right? At least 7 and another at least 7 and another at least 7. So it's still multiplication rule for the 4 flips. And we end up with this probability, which is about 150 times more probable than the other one, right? Which makes a little bit more sense. It's still pretty low, but we actually had, an intuitive sense that it was going to be a low probability anyways. This number seems to kind of match intuition a little bit better anyways. So now that we have our number here, this one, we can go back and say, was the coin game fair? We can look at this balance. We can say, this is still a probability less than, 1/10 of 1%, or is the game unfair? Between these two, I think I might choose the game is not fair. Right? This probability of occurrence just seems so low. I'm not going with that. I'm not buying it. That's just too unlikely. I'm going with the game is not fair. And that judgment is exactly what you do in hypothesis testing. So what we're concluding is that the game wasn't fair. The chance of the random event was sufficiently low that we didn't think that it was due to chance. Now, like it says, the only problem here is there is a small chance, less than 1/10 of 1%, but there is a chance we're wrong. The game might be fair. Improbable events do occasionally happen, just not very often. So can we be absolutely 100% sure? I guess no. But we can be 99.912% sure, which is pretty good. But the question is, if we are starting to get a little bit more fine-tuned about this, what does sufficiently low mean? That's kind of a nebulous term. What is sufficiently low? That brings up the concept of significance level, which is usually represented with an alpha. That's an alpha. And this is the probability which is chosen as the boundary. It should be chosen before you do your analysis. And it's somewhat arbitrary, but the typical values which are used is either 5% or 1%, but others can be used. How do you know whether you should use 5% or 1%? Well, it kind of depends on the situation. What's the need? If we're talking about coins, I suppose, or one of the other videos we were talking about snowballs, well, that's not really crucial. 5% would probably be fine. If we're talking about like a nuclear reaction, and we really want to be sure, we want to use 1% or maybe even less. So it depends on the situation, what your significance level is. And you actually don't have to set a significance level at all necessarily. You can simply get the probability and make an argument. It can be actually done either way. Let's do an example. So mosquitoes in Alaska. I've been told that the mosquito is known as the state bird for Alaska because they're so big. So we want to test that. We have this hypothesis that mosquitoes in Alaska are bigger than in the continental U.S. So we know that in the continental U.S., a collection of 500 mosquitoes will weigh a certain amount. And we have had enough studies done that we're actually very sure about the population in the continental U.S. We actually have the population mean and the population standard deviation. We feel very confident in those numbers. Now we take a sample of 500 mosquitoes in Alaska, and we get a higher mean, and we have a sample standard deviation from our sample. Now the question is there sufficient evidence to say that Alaskan mosquitoes are really larger? Now this is the same question as the coin game. Was there sufficient evidence to tell us that the coins were unfair. So, because, even if the Alaskan mosquitoes weren't bigger, there's a chance that, one particular sample would be, heavier anyways. And that's what this pretty much says, right? It's just due to random chance. So we need to do some calculations of probability and set this up, and in subsequent videos we're going to get into that detail. Really, at this point in time, just looking at the concept of hypothesis testing. So we have our sampling distribution. That's something that you should have already learned about in previous videos. All right, we know that the center of the sampling distribution is the population mean. So we have a population mean. We can plug that in. Now we have the sample mean of 26.1. We have to kind of figure out where that might be. It's certainly going to be higher. All right, we can look at it maybe over there. And that's just an estimate. What we need is our measure of spread. And that gets us, our standard deviation of sample means. And then we could do it much more precisely. But for the moment, we're just going to do a ballpark what if kind of scenario. And here's the what if. Right? We have this higher sample. One of two things. Again, it's like the coin game. Either there's really no real difference, and the terminology which is used is there's no statistically significant difference between the sample and the population, because of course you could subtract and there is a difference here. But statistically, it's just due to random chance, right? No big deal, right? If you take a sample in Alaska, it turned out to be heavier. That can happen. Or the Alaskan mosquitoes are in fact heavier. Right? One of the two is what our conclusion will be. So it's either due to random variations or not. If, and again, the actual calculations I'm going to do in another video. This is just concept. If it turns out that the probability of getting 26.1 grams as a sample is 7.2% chance, well, 7.2%, that's above our 5%. Again, this, mosquitoes is not really, high stakes kind of thing, so maybe we use 5% as the significance level. 7%, if that was the case, I'd probably say there's no statistically significant difference, and really Alaskan mosquitoes are no different than continental mosquitoes. If, on the other hand, we reset our balance, and if the probability of getting 26.1 grams is maybe 1.4%, well, that's certainly less than 5%, which is the significance level we were talking about. So that's pretty unlikely. So I would probably go with the fact that the Alaskan mosquitoes are in fact bigger. This balance and deciding between the two and using the probability to help you decide, that is the concept of hypothesis testing.